Assalamualaikum to Doctor and my friends. Today, our group will be presenting the Discrete Structure project with title Path and Circuit. Before we begin, let's introduce ourselves first. My name is Nur Zafira Izzati binti Ramzi and my matrix number is 206086.
Hi, my name is Samir binti Jasni. My matrix number is 207684.
Hello everyone, I'm Ahmad Faisal bin Fazil and my metric number is 209-292.
Hi, my name is Hana Jasmine and my metric number is 207058.
Okay, now let's start our presentation. In brief, this is the content of our presentation, which are the introduction, Euler circuit and Euler path, Hamilton circuit and Hamilton path, then the applications of the Euler circuit and Euler path, lastly the applications of the Hamilton circuit and Hamilton path. We'll take a look at the brief introduction first. In this topic, it is very important for us to know the definitions of circuit and path. So, what is circuit and what is a path? A circuit is a path that starts and finishes at the same vertex. What about the path? A path is a sequence of edges that begins at the vertex of a graph and travels from vertex to vertex along the edges of the graph. Now, I'll explain to you the Euler circuit and Euler path. Firstly, let's take a look at the Euler circuit. What is an Euler circuit? Before that, please be reminded that G is a graph. An Euler circuit for G is a sequence of adjacent vertices and edges in G that contains at least one edge. It must be a closed circuit. What is a closed circuit? A closed circuit means that it must start and ends at the same vertex, just like I mentioned before in the circuit's definition. Also, it must use every vertex at least once and use every edge exactly once and not more than that. Now that I already explained the definition of an Euler circuit, let's take a look at the example. So, based on the definition, we must identify all the characteristics that this graph G must have, which we must check whether G is a sequence of adjacent vertices and edges in G. Does it contain at least one edge? Does it start and end at the same vertex? Did graph G use every vertex at least once? And lastly, does it use every edge exactly once? We must check all of this to decide whether it is an Euler circuit or not. Now, let's check together. So, this graph G is a sequence of adjacent vertices and edges in G. Yes, it contains at least one edge. It also starts and ends at the same vertex, which the graph G starts at vertex E and ends at vertex E. As you can see in the diagram, this graph uses every vertex at least once. Also, it uses every edge exactly once. Thus, we can know that it is an Euler circuit. Next is Euler circuit theorem, which stated that a connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has an even degree. So we'll use the same example I showed just now. We have already checked these 5 characteristics based on the definition. Now we must also check whether each of its vertices has an even degree. As you can see in the diagram, I already counted the degree of each vertex. Clearly, every vertex has an even degree, which vertex A, B, C, and D have a degree of 2. Meanwhile, vertex E and F has a degree of 4. Based on the definition and theorem, it is confirmed that this is an Euler circuit. Now I'll be explaining Euler path. What is an Euler path? An Euler path can be defined such that G be a graph, V and W are two distinct vertices, and Euler path from V to W is a sequence of adjacent edges and vertices that starts at V and ends at W, passes through each vertex of G at least once, and traverses each edge of G exactly once. Also, it is not required to return to the starting vertex. Why? Because it is the path, not the circuit, remember? Now that I already explained the definition of an Euler path, let's take a look at the example. So, based on the definition, we must identify all the characteristics that this graph G must have, which we must check whether F and E are two distinct vertices. Is it true that from F to E is a sequence of adjacent edges and vertices that starts at F and ends at E? Does it pass through every vertex of G at least once? And lastly, does it traverse every edge of G at exactly once? We must check all of these to decide whether it is an Euler path or not. Now, let's check together. It is true that F and E are the two distinct vertices. It is also true that from F to E is a sequence of adjacent edges and vertices that starts at F and ends at E. This graph did pass through every vertex of G at least once, and it did traverse every edge of G exactly once. Thus, we can say that it is an Euler path. Next, I will explain Euler's path theorem. This theorem stated that a connected multigraph has an Euler path but not an Euler circuit if and only if it has exactly two vertices of odd degree. To have more understanding about this, I'll use the example I showed just now. We have already checked these four characteristics based on the definition. Now, we must also check whether there are exactly two vertices of odd degrees. As you can see in the diagram, I already counted the degree for each vertex, and we can see that vertex E and F has an odd degree of 3. Therefore, it is true that this graph G is an Euler path based on the definition and theorem. That's all for the Euler circuit and Euler path. Next.
Today I am going to present about Hamilton circuit and Hamilton path. So, what is Hamiltonian circuit? Okay, Hamiltonian circuit is the circuit that visits every vertex once, and it must start and end at the same vertex because it is a circuit. And okay, let's look at this example. We can see that it starts at the vertex A, and then it visits vertex B, vertex C, D, E, F, G, H, I, J, K, L, M, N, vertex O, visit vertex P, and then Q, and then R, and it goes back to vertex A. And there's no nice theorem that allows us to instantly determine whether or not a Hamiltonian circuit exists for all graphs. Okay, next, what is Hamiltonian path? Okay, Hamiltonian path also visits every vertex once, but does not have to start and end at the same vertex. For example, a delivery person wanting to stop at every delivery location rather than going down every street. Okay, now let's look at this graph. Okay, it starts at vertex A, and then it visits vertex D, and then it visits vertex G, vertex H, and then vertex E, vertex B, and then C, F, and it ends at vertex I. From this, we can see that it visits every vertex, but it does not end and start at the same vertex. Next, okay, this is the example of a no Hamiltonian circuit. Okay, a no Hamilton circuit is a graph with a vertex of degree 1, and it cannot have a Hamilton circuit. Let's look at this example, the graph G. We can see that from this graph, the vertex E only have a degree of 1. Next example is this graph H. Okay, this graph H, okay, let's look at the vertex. Let's start at the vertex A, and then we move to vertex B, and then vertex C, and then we visit vertex D, and we visit vertex E. So in order to be a Hamilton circuit, it needs to end and start at the same vertex. Just now we start at vertex A. So in order for us to go back to vertex A, we must visit vertex C once again, which is we already visit vertex C twice. So this is not a Hamilton circuit because Hamilton circuit only needs to visit all vertex once. So okay, no Hamilton circuit can exist in H. For any Hamilton circuit would have to contain 4 edges. Next, okay, Dirac's theorems. Okay, Dirac's theorem said that if G is a simple graph with n vertices, with n greater than or equal 3, such that the degree of every vertex G is at least n over 2, then G has a Hamilton circuit. Okay, let's look at the example. We can see that this graph has a degree of 3. Vertex A has degree of 3. Vertex D has the degree of 3. Same goes to vertex D and vertex B. So based on Dirac's theorem, if the degree of the vertices is greater than or equal than half of the number of the vertices, okay, now we can see that the number of vertices have here is 4 and half of 4 is 2. So since every vertex is degree of 3, therefore the degree of the vertices is greater than half of the number of vertices. Therefore, this graph is this graph has a Hamiltonian circuit. Next is Orr's theorem. Okay, Orr's theorem said that if G is a simple graph with the n vertices with n greater than or equal 3, such that the sum of degree u and degree v greater than n for every pair of non-adjacent vertices, u and v is in G, then G has a Hamiltonian circuit. Okay, let's take a look at this example. We can see that this graph. Okay, what does it mean by non-adjacent vertices? Is vertices that does not directly connected, like A and D, B and C, B, E, and D, A. So now we add. Let's add the sum of the degree of the vertices. Like AD is we have A has degree of 3, and then D has degree of 3, and then 3 plus 3 is 6. And then BC has the sum of degree of 5, BE also 5, and DA is 6. Okay, so the sum of degree of every pair of non-adjacent vertices is either equal or greater than 5, like from this example, which is 5 and 6, and which is the number of the vertices which is greater than or equal to 5, which is the number of vertices which is 5. Therefore, the graph has a Hamiltonian circuit. But if the condition of does not present in the graph, it does not mean that the graph is not Hamiltonian. If the condition of Dirac's theorem or Orr's theorem does not present in the graph, it does not mean that the graph is not Hamiltonian. Okay, that's all. Thank you.
Okay, in this section, we'll be talking about the applications of Euler paths and circuits. Okay, problem arise regarding the issues of efficiency in traversing in real-life applications. This problem can be solved by modeling the problem into a graph, then applying Euler path or Euler circuit. Example, if a postman is able to find Euler path that represent the streets, he won't have to travel to the same street twice. The famous Königsberg bridge problem inspired a Swiss mathematician, Leonhard Euler, to come up with a solution. Okay, this is an example from what we discussed earlier regarding the postman. Okay, suppose that a postman has to travel through over every edges exactly once in order to deliver items and finish traveling at the starting point to maximize efficiency. How he would have done it? Here's the solution. Okay, we know that it is the Euler circuit since all of the vertex have even degree. One of many alternatives is the postman can travel through A to E and then back to A to B to C to B to E to C to D to E and then to F, to D, to F, and then back to the starting point A. This all can maximize the efficiency. Okay, in some cases, if there is no Euler's path, the way to find the problem shortest path or circuit is using route inspection problem. But bear in mind that whenever a graph has an Euler circuit, it is always the optimal solution. Okay, this problem posed by a Chinese mathematician named Guan Meigu in 1962. Okay, this is an example of the problem. Okay, a postman has to find the shortest way to travel every edges represented in this graph, but Eulerian circuit does not exist. Help him find the cheapest route across all the points. As you can see here, the numbers represent the length. Okay, this is the solution. So we need to assume a starting point. So in this solution, I have chosen the point A. Okay, first step is to highlight all degrees vertex. Okay, in this graph is B, C, D, and E. Okay, second step is to pair an odd degree vertex with the other one and find the shortest length. Okay, as example, I've chosen the point B, to be paired with the other points. So A, B, C, B to C, and then so when we already paired B with C, D and E have to be paired together. Okay, so B, B to D, and then C, B to E. Okay, after that, we have to total up everything from, okay, example A, B, C, 3, plus 4, and the total is 7. So B total is 6, C total is 12. So you have to again remember that we have to find the shortest length. Okay, as example, at B, okay, B to D, the most straightforward point, the most straightforward length is, you can see, is straight from B to D is 5. But we need to find the shortest length, so we have to go via A. Say 1 plus 2 is equal to 3. So we have to choose that, the shortest length. Okay, okay, the fourth step, okay, we need to choose the smallest total, okay, and add it with the total length of the entire graph, which is 24. So we have the product 30, and 30 is the smallest possible length. Okay. So this is the way to find the route. Okay, in finding the route, you have to remember that we have chosen the B, the smallest, B and D. So you have to repeat B, D, and C with E. You have to repeat both. Okay, and you have to remember too that the total length is 30. So we have to create a route around that clues. So one example that I can find here is through A to B, and then to C to F, and then to C again, and to E, to F, and back to E, and then to D, then to B, to A, D, and back at the starting point A. Okay, so this is the solution to the route inspection problem. Okay, that's all for me. Thank you.
So today I'm going to tell you about the applications of Hamilton circuit and Hamiltonian path. First, real application of Hamiltonian path and circuit. Hamiltonian circuit and path have real application in real-life problem. As an example, scientists use Hamiltonian path and circuits when mapping genomes. But we are not going to talk about that. In a less complicated application, Hamiltonian path and circuits are used when we want to find the best route when traveling from place to place. The famous problem is the traveling salesman problem, where we should find the optimal Hamiltonian circuit with the lowest weight total. Okay, this is the example of traveling salesman problem. Suppose a salesman needs to deliver his package in 4 cities. He looks up the airfares between each city and puts the cost in a graph. In what order should he travel to visit each city once, then return to his office, which is A, with the lowest cost? So, there are many solutions that we can use to solve this problem. First is brute force algorithm. Okay, there are 3 steps that you can use to solve this using brute force algorithm. First, list all possible Hamiltonian circuits. Second, find the length of each circuit by adding the total weight. And third, select the circuit with minimal total weight. So first, as you can see here in the box, I have listed all the possible Hamiltonian circuit, which is ABCDA, ABDCA, ACBDA. And after that, we calculate the total weight. You can see the weight at the edges of the circuit. So you should take note that all other possible circuits are the reverse of the listed one or start at a different vertex but result in the same weight. From this, we can see that the last circuit is the optimal circuit but it is not suitable to use if number of vertex too high. The last circuit is the optimal circuit because the total weight is the smallest than these 2 circuits. Next, I'm going to tell you about heuristics algorithm. Heuristic works quite well in finding solution most of the time, but they are not always optimal. 2 main heuristics for finding minimum cost Hamiltonian circuits are nearest neighbor algorithm and sorted edge algorithm. First is the step to use nearest neighbor algorithm solution. First step is choose a vertex as a starting point, and from a starting point, choose the edge with the smallest weight. If there are more than one choice, then choose random. Continue build the circuit and make sure to visit all vertex once. Go back to the starting point to complete the circuit. Here are some examples. We use the same graph as before. Nearest neighbor algorithm. Okay, we start from vertex A, and from here we can see the nearest neighbor is vertex C with total weight 20 rather than D 30 and B 70. So we choose C. From C, the nearest neighbor is D with weight 10 rather than B with weight 15. So we choose D. From D, our only option is B. We cannot choose A because it will not form a Hamiltonian circuit. It must go past B. So from D, we go to B, and to complete the circuit, we need to get back to A. So from here, the result of the circuit is A, C, D, B, A, and the total weight is 150. By using this algorithm, we end up using the worst circuit of the graph with the biggest cost needed because nearest neighbor algorithm is a greedy algorithm and it only looks at the immediate decision without considering consequences in the future. By using route A, C, and CD, we are forced to use expensive route BA later. Next is sorted edge algorithm. Sorted edge algorithm is about we sort the most cheapest edge in the graph first. So first, the step is select the cheapest unused edge in the graph and repeat step 1, adding the cheapest unused edge to the circuit unless adding the edge would create a circuit that doesn't contain all vertices, or adding the edge would give a vertex degree 3. Repeat until a circuit containing all vertices is formed. Okay, these are the example. First, the cheapest edge are CD with weight 10. As you can see here, CD, I already highlight it for you. Next cheapest edge are CB with weight 15. Here. C, D, and C, B. We're going to highlight it because we're going to use it later. Then the third cheapest path are AC with weight 20. But we cannot choose that because vertex C will have degree 3, which is not allowed in Hamiltonian circuit, so we need to choose AD path with weight 30. Then we cannot choose BD to complete the circuit because that will make D have degree 3. So the only path that we can choose are B, A. So we come to the result ADCBA with the total weight 125. Sorted edge algorithm overcomes some of the shortcomings of nearest neighbor algorithm, but it's still a heuristic algorithm and did not give the optimal result. So as a conclusion, uh, brute force algorithm will result for the most optimal circuit with the smallest total weight. But it is disadvantage to use brute force algorithm if the number of vertex is too many. That's all. Thank you.
This slide shows the references that we use for our project. Yes, that's all for our presentation today. Thank you.